In this video, we explore the wave nature of matter, and especially the wave nature of electrons, and examine the implications for how electrons are arranged around a nucleus. In other words, the implications for the electronic structure of atoms. Many people are surprised when they hear that Albert Einstein won his only Nobel Prize not for his work on the theory of relativity, but for his work in mathematically and physically describing the phenomenon of the photoelectric effect. He published this work in 1905 and was awarded the 1921 Nobel Prize. The photoelectric effect involves the emission or ejection, if you like, of electrons from a surface when light or electromagnetic radiation of certain frequencies is shone upon that surface. We can represent that diagrammatically. Incoming light waves hit the surface of a material, causing electrons to be ejected or emitted from that surface. They can be accelerated towards a positively charged plate to create an electric current in an external circuit. And since that electric current was created by light, we call it a photoelectric current, hence the name photoelectric effect. Now in this animation we have represented the incoming light as waves, and in Einstein's time light was considered to be a wave as it conformed to the known properties of waves in being able to be reflected, diffracted, refracted, and being able to set up interference patterns. The problem was there was no explanation as to how waves were able to impart their energy to electrons to explain the observed phenomena. It was especially difficult to explain why photoelectric currents were only observed above certain threshold frequencies of the incident light. Einstein's big conceptual leap was to imagine or describe the incoming light waves as tiny packets of energy called photons. The energy of an incoming photon can be transferred to an electron to raise its energy in pretty much the same way as colliding particles can transfer energy to each other. If the energy of the photon is high enough, it will eject the electron from the atom and the photocurrent is produced. And only by describing light in particle form was Einstein able to explain the photoelectric effect. 16 years after Einstein's explanation of the photoelectric effect, the French physicist Louis de Broglie reasoned that if light waves could exhibit particle-like properties as described by Einstein, then maybe particles, including electrons, could exhibit wave-like properties. And the de Broglie relationship is mathematically represented by this equation here, where lambda is the wavelength, p is the momentum, and h is the Planck constant, which has the value 6.63 by 10 to the minus 34 joules per second. Now, since momentum is equal to mass times velocity, you may also see this equation expressed like this as the wavelength equals Planck's constant divided by mass times velocity. The de Broglie relationship can be used to calculate the wavelength of everyday objects that we would classically consider as particles. So, for example, we can calculate the de Broglie wavelength of a cricket ball. Now, the mass of a cricket ball is 156 grams or 0.156 kilograms. A fast bowler can bowl a ball at speeds of around 150 kilometers per hour, which is 41.7 meters per second. When we plug those numbers into the de Broglie relationship, we get a wavelength of the order of 10 to the minus 34 meters. And these wavelengths are simply too small to be detected by modern instrumentation. And this is part of the reason that we don't observe the wave-like properties of everyday objects. The large mass results in wavelengths so small that the properties such as refraction and diffraction of a cricket ball cannot be observed. However, with particles of very small mass, such as electrons, the de Broglie wavelength is of the order of 0.1 to 1 nanometer, depending on the energy of the electron. And these wavelengths are able to be observed and detected by modern instrumentation. And in fact, the wave-like properties of electrons were confirmed in 1927 when it was shown that a beam of electrons could be diffracted through a crystal lattice to show an interference pattern on a detector, and these interference patterns are definite wave-like properties of electrons. So, what are the implications of wave-particle duality for the electronic structure of atoms? Well, the main implication is that we can never be sure of the exact location of an electron. In classical physics, particles occupy a particular location, and you can specify the position of a particle. Waves, however, are dispersed throughout a region of space. So in quantum physics, the electron particles, which have wave-like properties, are actually distributed through space and not confined to a particular location. In the Rutherford and Bohr models of atoms, we talk of electrons circling the nucleus in discrete orbits, pretty much analogous to planets orbiting the sun. And this so-called solar system model of atoms can often lead to misconceptions when it comes to a physical understanding and a physical description of atoms, because in such classical descriptions of the atom, both the position and the energy of an electron can be determined with high accuracy and high precision. However, in the modern quantum mechanical description of the atom, this is not the case, and we do not talk of discrete orbits, but rather we talk of orbitals, and an orbital being a region of space where there is a high probability that an electron exists. And orbitals describing both the energy and the distribution of an electron in space, rather than the exact position of that electron. So typically the energy of electrons is known with high accuracy, but the position is not. And the location of an electron around a nucleus is often shown using density probability plots such as these, where regions of high density of dots or shading indicate a high probability of an electron being found in that region of space, and regions of low density dots or shading representing a low probability of finding an electron in that region. So we use atomic orbitals to describe the overall energy of electrons around nuclei in atoms, and to describe the region of space in which an electron particle wave is likely to exist. Now, each orbital, remember an orbital is just a region of space, has a characteristic energy, a characteristic shape, and a characteristic orientation around the nucleus. And each of these characteristics is given a label to assist in describing the distribution of electrons around a nucleus. And these labels are called quantum numbers, with the quantum number n describing the overall energy of electrons within an orbital, the quantum number L describing the shape of the distributions of electrons within an orbital, and the quantum number ML describing the orientation of the electron distribution around a nucleus. And finally, orbitals are said to exist in subshells and shells. And we'll develop these ideas a bit further. But for now, at this stage of your chemistry study, a lot of this information will be new, counterintuitive and abstract, and therefore potentially confusing. In all of these descriptions of electrons and electron clouds and the electronic structure of atoms, etc., it's worth remembering that an orbital is simply a region of space. It's a region of space where there's a high probability that an electron exists, and a region of space that has a particular energy, a particular shape, and a particular orientation. Nevertheless, it's still just a region of space. In the following video, we'll look at the relationships between orbitals, subshells, and shells, and also use the quantum number labeling system to assist with our growing understanding of the electronic structure of atoms.